On the 13th of January 1920, the editorial page of the New York Times took a moment to mock a quiet physics professor from Massachusetts. The man, Robert Goddard, had published a modest paper suggesting a rocket could one day reach the moon, and the newspaper explained to its readers that this was impossible. A rocket in the vacuum of space, it declared, would have nothing to push against, and therefore could not move. The professor was said to lack the knowledge handed out daily in high schools. Goddard was right, and the newspaper was wrong, and the correction ran 49 years later, 3 days after Apollo 11 left for the moon, when the Times printed a short note admitting the error. The strange thing is that the mistake in that editorial is the exact same mistake almost everyone still makes about how a rocket works. The misunderstanding is worth naming precisely because it is so natural. Watch a rocket lift off, and it looks obvious that the flames are pushing down against the launch pad, shoving the machine upward, the way a hand shoves off a wall. If that were true, then in space, with no pad and no air to push against, the rocket would be helpless. But that is not how it works, and it never was. A rocket does not push against the ground or the air, it pushes against itself. The man who first turned this into real mathematics was not an engineer at all, but a nearly deaf Russian schoolteacher named Konstantin Tsiolkovsky, working alone in a log house far from any laboratory. Around the turn of the 20th century, decades before anyone flew a rocket, he wrote down the equation that still governs every launch, a formula relating how fast a rocket can go to how much of its weight is propellant, and how fast it throws that propellant out the back. He did it for the love of the problem, with no funding and no audience. And he understood before anyone that the tyranny of the fuel was the central obstacle. Every rocket engineer since has worked inside the boundaries that quiet schoolteacher drew. The real principle was written down more than 300 years ago by Isaac Newton, and it fits in one sentence. For every action, there is an equal and opposite reaction. Fire a bullet from a gun, and the gun kicks back into your shoulder. The bullet goes one way, the gun goes the other, and nothing outside the two of them is involved. A rocket is a gun that never stops firing. It throws mass out of its back end at tremendous speed continuously, and the equal and opposite kick throws the rocket forward. The exhaust is the bullet. The rocket is the recoil. It works in empty space precisely because it needs nothing to push against except the stuff it is throwing. The stuff it throws is the whole game, and this is where the difficulty begins. To get that violent backward jet, a rocket burns fuel to make an enormous volume of hot gas and forces it out through a nozzle at the back. A car engine does something similar, but a car has an unfair advantage a rocket does not. A car burns fuel using oxygen it sucks freely from the air around it. A rocket climbing toward space cannot count on air because 100 miles up there is none, so it must carry its own oxygen with it in tanks alongside the fuel. That single requirement, hauling your own oxygen, is the reason rockets are the way they are. There is one measure engineers use to judge how good a propellant really is, and it is worth understanding because it explains almost every design choice. They call it specific impulse, and the plain language version is simply this: how much push you get out of each pound of propellant before it is gone. A more efficient propellant throws its exhaust out faster, so every pound does more work, so you need fewer pounds. So the vicious weight spiral eases a little. The difference between a good propellant and a mediocre one, measured this way, can decide whether a rocket reaches orbit at all or falls short by hundreds of miles per hour. Chasing a few percent more of this single number has consumed entire careers, because in the arithmetic of rockets, a few percent is the margin between success and a crater. If you have ever stood near a launch and felt it in your chest before you heard it, you have met the consequence of that requirement without knowing it. The reason a rocket is almost entirely tank, the reason it is the size of a building to lift a capsule the size of a car, is that most of what you are looking at is not machinery. It is propellant, the fuel and the oxygen to burn it, and there is a staggering amount of it. For many rockets, something like 9/10 of the total weight sitting on the pad is propellant that will be gone in minutes. You are not watching a vehicle with a fuel tank. You are watching a fuel tank with a small vehicle on top. That imbalance creates the cruelest problem in all of engineering, and it feeds on itself. To lift a heavy load, you need more propellant, but propellant is heavy. So now you need even more propellant just to lift the propellant. Add fuel to go higher, and the added fuel weighs the rocket down, demanding still more fuel to lift that. The math turns vicious quickly. This is why building a rocket that can reach orbit is so brutally hard, and why, for decades, it sat at the very edge of what was possible. Every extra pound of spacecraft at the top can demand many pounds of propellant at the bottom. The solution to that trap is the single most important idea in rocketry, and it is beautifully simple. You throw the rocket away as you go. This is called staging, and it works like this. Stack 2 or 3 rockets on top of one another. The big one at the bottom fires first, burns all its fuel, lifting the whole stack off the ground. And then, instead of coming along as dead weight, it detaches and falls away entirely, empty tanks and heavy engines and all. Now, a much smaller, lighter rocket is already high and fast, and it lights its own engine, carrying none of that spent weight. Drop the dead mass the instant it stops being useful, and each remaining stage has far less to push. Every rocket that has ever carried humans to orbit has done it by throwing most of itself away on the way up. The usual story is that once we understood the physics, rockets were basically a solved problem, a matter of building bigger versions of a known thing. That story does not survive the launch failures. The principle Newton wrote down is simple, but making it survive contact with reality is savage, because a rocket is a controlled explosion you are trying to ride. The propellants are often violently reactive, chilled hundreds of degrees below zero, or corrosive enough to eat through metal. The engine must burn them at pressures and temperatures that would destroy any ordinary machine, feeding them in through pumps that move tons of liquid every second. For most of the history of spaceflight, the normal result of all this was that the rocket exploded, and the engineers learned by counting the wreckage. Not all propellants are equal, and the choice defines the whole machine. The cleanest and most powerful common pairing is liquid hydrogen burned with liquid oxygen, which throws its exhaust out faster than almost anything else and leaves only water vapor behind. But hydrogen must be chilled to more than 400 degrees below zero to become a liquid, and even then it is so light and thin that its tanks must be enormous, which is why hydrogen rockets look bloated and swollen. Kerosene, essentially a refined lamp oil, is denser and easier to handle and packs more punch into a smaller tank at the cost of a little efficiency. A third family, the storable propellants, will sit for years at room temperature and ignite the instant they touch each other, which makes them perfect for missiles and spacecraft that must fire on command, and dangerous enough that they are often lethally toxic. Every rocket is an argument about which of these trade-offs to accept. There is also a fork in the road between two entirely different kinds of rocket, and you have seen both. A liquid rocket carries its fuel and oxygen as liquids in separate tanks and pumps them into the engine, which means it can be throttled, shut down, and restarted, like a car with a gas pedal. A solid rocket, by contrast, is closer to a firework. Its fuel and oxidizer are pre-mixed into a rubbery solid packed into a tube. And once you light it, it burns until it is finished, with no throttle and no off switch. Solids are simple, cheap, and immensely powerful, which is why they are strapped to the sides of many launchers for extra shove at liftoff. But their all-or-nothing nature is exactly what makes them unforgiving. The choice between the two is a choice between control and simplicity. The engine is where the real war is fought, and its problem is heat. Inside a large rocket engine, the burning gas reaches temperatures hot enough to melt the very metal the engine is made of, and it does this continuously for minutes at a time. An engine that melts its own walls in the first second is useless. The trick that makes it survive is quietly clever. Before the fuel is burned, it is often run through thin tubes wrapped around the outside of the engine bell, carrying away the heat and keeping the metal below its melting point. And only then is that same fuel fed into the fire. The freezing propellant on its way in is what keeps the blazing chamber from destroying itself. The engine is cooled by the very thing it is about to burn. Feeding the fire is a hidden feat that few people ever think about. To keep a large engine burning, propellant must be forced into the combustion chamber faster than a fire hose could ever manage, against the ferocious pressure of the flames already inside. And this job falls to a pump spinning at tens of thousands of revolutions per minute. The pump on a big engine can be smaller than a person, yet generate the horsepower of a locomotive, driven by its own miniature engine burning a little of the same propellant just to run the pumps. There is, in effect, a rocket engine inside the rocket engine, whose only purpose is to shove the fuel forward fast enough. When these pumps fail, and for years they often did, they can tear an engine apart in less time than it takes to blink. Steering is its own puzzle because a rocket has no road and no wings that matter. It cannot turn by leaning against the air the way an airplane does, especially once the air runs out. The answer on most large rockets is to swivel the engines themselves. The entire nozzle throwing out its jet of fire tilts a few degrees one way or the other, and pushing the exhaust slightly sideways nudges the whole towering machine to pivot. A rocket steers by aiming its own recoil. It is the same reason you can point a garden hose and feel it try to twist in your hands, scaled up, to move a vehicle weighing millions of pounds. Then there is the question of speed, and the numbers are the part that never stops being astonishing. To fall around the Earth in orbit rather than falling back down, a spacecraft must travel sideways at roughly 17,500 miles per hour, about 20 times faster than a rifle bullet. Reaching that speed is what all the propellant is really for. Getting up high is the easy part, a matter of a few minutes of climb. Getting going fast enough sideways to stay up, to keep missing the ground as you fall, is where nearly all the energy goes. Orbit is not really about altitude at all. It is about going sideways so fast that you fall forever and never arrive. Once a spacecraft is up there and moving fast enough, a stranger truth takes over, and it overturns everything the ground taught you about motion. In orbit, there is no air to slow you down, so there is nothing to push against, and nothing to coast to a stop. A spacecraft does not need its engine running to stay up, any more than the moon needs an engine. It simply falls around the Earth forever, engine off silent, because there is nothing out there to rob it of its speed. This is why astronauts float. They are not beyond gravity, which is nearly as strong up there as on the ground. They are falling constantly, along with their spacecraft, and falling together feels exactly like weightlessness. Changing course up there is its own counterintuitive art. With no air and nothing to lean on, the only way to change your path is to fire an engine and throw more mass backward. And a tiny push produces effects that seem all out of proportion. A brief burn lasting seconds can raise the far side of an orbit by hundreds of miles, hours later, and thousands of miles away, because in the frictionless dark, nothing ever bleeds the change away. Spacecraft do not steer so much as nudge, spending small, precise squirts of propellant and then waiting, sometimes for hours, for the geometry of the whole orbit to swing them where they want to be. Out there, patience is a form of navigation. Coming home reveals the hidden twin of the whole problem, and it is that same terrible speed in reverse. A returning spacecraft is moving at those same thousands of miles per hour, and all of that energy of motion has to go somewhere before it can safely land. It goes into heat as the vehicle slams into the thin upper air and compresses it into a shock wave hotter than the surface of many stars, wrapping the capsule in a sheath of glowing plasma. The heat shield that survives this is not fighting the temperature so much as feeding it, often built to slowly char and flake away on purpose, carrying the heat off with the pieces it sheds. The same speed that was so expensive to gain becomes a deadly problem to get rid of. For a long time, the deepest frustration in all of this was that a rocket was used exactly once. It clawed its way to orbit by throwing away nearly its entire self stage by stage, and every piece that fell away, the tanks, the engines, the pumps that cost fortunes to build, tumbled into the ocean and was gone. Imagine an airline that scrapped the airliner after a single flight, and you have the economics that made space so ruinously expensive for half a century. The physics demanded that most of the machine be discarded, but nobody had proven the discarded part could not, instead, be flown home and used again. Learning to land the falling stage upright on a jet of its own remaining fuel so that the most expensive piece could be caught and reused is the change that has quietly begun to break the old spiral of cost. The engineers who built the first rockets were not wrong about the physics, and Goddard, the professor the newspaper mocked, had it right in 1920. He understood that the reaction principle needed nothing to push against, built and flew the first liquid-fueled rocket in 1926, a small thing that rose barely higher than a house, and worked out staging and steering long before anyone took him seriously. He was not a crank who got lucky. He was a careful man who was simply decades early and who endured public ridicule with the quiet certainty of someone who had checked his arithmetic. The moon rockets that came later were his ideas grown enormous, and the engineers who built them freely admitted they were standing on the shoulders of a mocked professor and a deaf schoolteacher who had done the hard thinking first. None of the people who worked it out were wrong, and that is the quiet dignity of this story. Tsiolkovsky wrote the equation with no money and no rocket. Goddard flew the first liquid engine and was laughed at in print for his trouble. The generation after them turned those principles into machines that carried human beings to another world. And they did it, not by discovering some secret the pioneers had missed, but by paying, in exploded prototypes and lost fortunes, the enormous engineering price of making a simple truth survive in the real world. The idea was always sound. The bill for building it was staggering, and it was paid one failure at a time. The lesson buried in all of this reaches well past rockets. The thing that looks like the hard part, the fire and the noise and the flames pushing against the ground, is an illusion. And the person who understands the counterintuitive truth underneath, that the machine is only pushing against itself, is the one who can actually build it. The obvious explanation felt so right that a great newspaper printed it as settled fact, and it was completely wrong. The whole of spaceflight came from a handful of people willing to trust the strange arithmetic over the obvious picture. If you have ever watched a launch and felt deep down that the flames must be pushing against something below, you are in good company. Because that instinct is exactly the one the New York Times committed to print in 1920. The truth is stranger and simpler. Out there, with nothing to lean on and nothing to push against, a rocket climbs by, throwing part of itself away again and again, hurling mass backward into the dark so that what remains is carried forward. It needs the universe to provide nothing at all, which is precisely why it can go anywhere in it.